All right, let's get started. Good afternoon. So we kind of moved away from looking at how the object, various objects are, like in terms of video, audio, and games and stuff. And now we're trying to get a sense of how that affects systems issues, like operating systems, networks, and distribution, being able to play back and things like that, right? That's sort of the main focus of the course, and we're trying to understand those issues. So I started off by giving a little bit overview of networking, right? I mean, obviously I had to take a network class to get the whole sense of what's going on, but sort of a big, like 10,000 feet or 100,000 feet kind of view, right? So one of the things I mentioned was there's this tension within the networking community whether you should go with something like a circuit switch kind of stuff where you kind of define what the path is end to end, right? You sort of define, a good example is a telephone line. So if you have the old-fashioned telephone line, you establish a connection between those two endpoints. And once you establish a connection, once you get the line, you're sort of guaranteed what bandwidth you want, right? And that sort of works. It's kind of elegant, but it's also very wasteful because what happens is most of the time they're silent. There's no data going through, and you can't. It's not also elastic. It can't take more stuff. So you would like something else. And so the modern internet is based on a packet switch model, where each packet sort of figures out how to get to the other end, and that means that you get good performance, or sometimes maybe not so much. So you have two different ways of using it. In terms of one of the two models I mentioned was UDP and TCP, and one of them gets you the reliability and stuff that you sort of maybe used to in a circuit switch kind of fashion, and the other one is a UDP where you get whatever the network can give you, right? The other thing that they really worry about is the notion of fairness. Because if the network can support any amount of traffic you can throw at it, then it's sort of uninteresting. What really happens is your network can only support a certain amount of traffic, right? Be it on the from your laptop or a cell phone to the network, which is usually called a last mile, right? So the bandwidth from his wireless laptop to the access point is limited. So he has to make sure that all the applications he's running on that machine would be able to share them in some sort of a fashion. And once you go beyond that, you begin to aggregate more traffic. So all the laptops in this classroom are probably going to go to the same access point, and all the ones from this building are going to probably go to the same line, and so on and so forth. So you need to have some way of figuring out how to split the, how to give the bandwidth to each of them, right? And I can't even scratch the surface of this stuff because this is essentially what networking boils down to, right? Because if you figure out the best way to do that for every kind of application, then life is good for networks. But it's ongoing research, and it depends on number of issues, like who's willing to pay more and what's the sort of issues. But at a very high level, you can think of it as there are two different ways. One is to kind of split them into some fashion and say you get certain amount and somebody else gets a certain amount and stuff. And there's still proponents who work in that model, and there's a lot of reasons why it can't work and a lot of reasons why it can work, right? Some of the reasons why it can't work is the issue of how to figure out. So it all works good if I can charge you something. So if I have a way of saying, I'm going to charge you $1 to be on the network for 1 hour. I'm going to charge you $10. So then I can kind of say he should get 10 times as much as him. But for a number of reasons, that's not feasible because the payment and all those things are not feasible to do. So just going by the network and trying to figure out what should get more bandwidth it's not a trivial task. How to know that he's the one I need to give more than somebody else, and all those things are fairly tricky. So the dividing equally sort of, there's still a community which wants to do that. There's still a need for doing that. There's still it works in specific cases, right? For example, we can say anything from debart low should get 1/10 of the bandwidth outside or something like that, but not to the end your laptop or device, right? So what happens is you kind of compete with the best effort, meaning you just send all the packets and see what kind of falls out on the other end, right? And that's sort of the best effort. That's sort of what the networks are built for. And so the idea of best effort is you just throw as much as you can, and maybe something will come out. And on average, you will get your fair share, depending on how much traffic you are pumping and kind of stuff, right? So the key here is on average, right? So which means that if I do this for a long time, statistically long time, then on average, I would get how much data I'm sending through. But what we don't operate in that kind of a time frame. So we want to know how much he's going to get, how much you're going to get, and so on and so forth, right? So we need to kind of get a sense of what this kind of traffic is, so we can kind of say how much you should get, and so on and so forth. So the networking community likes one model of traffic, which is TCP, and TCP considered to be nice, right? So how TCP internally works, right? And some people I've heard it talk about it as the TCP standard. And when you take networking class, you realize that there's no standard. It's just the way TCP was written, and we just kind of go with that model, right? So the way TCP works, each link, each network connection you create, tries to figure out how much bandwidth it can acquire on the network, right? So it doesn't know how much network there is. So it wants to figure out how much network it can achieve. So it makes an assumption that if a packet is dropped, it's being dropped because of congestion, not because of anything else. So they make an assumption that if a packet that I sent was not received on the other end, then there's something wrong. The network is fully congested. That means I need to reduce, right? So what they do is they try to probe it by basically trying to start from some number, let's say 1. And then I start sending 1, 2, 3, 4, and so on. I keep increasing how much I send. So I send 1, wait for acknowledgement. If it gets to the other end, then I assume that the network is fine. Then I send 2, then I send 3, then I send 4, and so on and so forth, till a point where I don't get, the network drops some packet. Then I assume that since it's dropped, that I'm going beyond what the network can support. And I try to be nice by dropping exponentially. So if I could send 99, but I fail at 100, I drop back to 50, and then I start counting again, right? So what happens is you have this sort of like a little staircase kind of thing going additively, and then you drop exponentially, right? You let's say you go to 100, then you drop to 50, and then you start doing, right, at some point then drop, and so on. So you see this sort of like a sawtooth pattern where TCP is trying to find what it's trying to do, right? So the assumption here is if there are multiple TCP sources within your system, then they're all paying nice because they try to probe the system as much as possible, and then they kind of back off. So at this point, presumably this is how much the network can support, but then it drops off, and then it tries to be nice, right? So that is the model that TCP shows. That's what TCP does. In contrast, something like a FTP application, which does UDP, doesn't have to follow this stuff. So if you build a FTP application, you can basically start off by sending, let's say, 1,000 packets per second, right? And let's say TCP did this and then found out that sort of something around 100 is what the network can support. UDP, like your application, can dump, like, say, 1,000. And there's nothing which prevents it. Regardless of what you do, only 100 is going to go through, but you're going to cause havoc because now you're kind of messing with the network. Now you're going to make TCP kind of react because TCP it's going to find that somebody is taking all the network. So bad things happen, right? So people like to look at TCP and say how good you are compared to that kind of a behavior where it's trying to be nice and all those things. And that's generally how the networking community sort of figures out how good your protocol is, because this is not considered to be good, so we can kind of say how good you are compared to that stuff, right? So in that sense, we would like to know how the multimedia traffic that we talked about looks like. The way it's referred to is it's called isochronous traffic, right? The three different ways of describing traffic is synchronous, right, or sort of like a constant traffic. So if you imagine sending some packet every so often, if you imagine sending a packet every second or so, or if you imagine sending like 100-byte packet every second, then it's called synchronous because you're sending the constant traffic throughout the interval, right? And if you hadn't done all this compression and stuff, video or one of the stream audio would look like asynchronous traffic. If you're doing a 30 frames per second, you expect 1 frame every second, or 1 frame of the same size every second. So you sort of expect this sort of a synchronous traffic, right? So the nice thing about synchronous traffic is you sort of define when this traffic is going to come. So it may come and certain bursts every so often, right? So this time between bursts may be constant, and this magnitude would be constant, which means that you sort of know how much it's requiring on the network, right? So you can get a sense of how this will react with the TCP or something, but you know how much bandwidth you have to give, right? The asynchronous kind of traffic, they just come whenever they feel like, right? So I can't really predict what will happen. So they may come as I may see some traffic here, none at all for a while, and then I get like lots of traffic. So I may use some traffic, or some of the time I may use no traffic at all, right? So you can give an example of like web browsing, where you probably go to you click on the link, then you get a whole bunch of data, and then nothing is happening. So you're sort of unpredictable. You sort of dealing with whatever the user is doing, right? In the case of isochronous traffic, it's sort of in the middle, right? It's not exactly predictable, but it's also sort of comes all the time, right? So, and you can see why you would call it isochronous, right? If you think of the IB and P frame, right? So you sort of get the I frame every so often, which tends to be pretty big. And then you have the B and P frame, which may tend to be very small. And the network may kind of bunch a couple of these B frames together because they're small enough. So you have this kind of stuff where it's sort of regular, but not quite. You know, you may not figure out what's going on, right? And the other nice thing is, throughout this stuff, the multimedia traffic, they tend to do two things. One is they tend to ask for a certain amount of bandwidth, but not more than what it wants, right? So, for example, if you had a 1 Mbps DSL at home, right? And you want to send a 10 kbps video, right? For the most part, your 10 kbps video would be fine, right? It's not going to grow to fill that space. It's just going to be happy with what it has, right? Whereas if you talk about these TCPs, it'll try to grow to capture that 1 Mbps. The UDP will try to go to capture the stuff. So even though this one is sort of predictable, sort of unpredictable, it doesn't go beyond a certain amount, because that's what they have to do. So you don't have, when you're talking about fairness and stuff, you don't have to worry about them taking all the bandwidth, right? There's a constant traffic, but they bound themselves to some aspect. And the other thing they do is most of them would react to the network conditions. So if there's a network packet drop or something, they can change the network to, let's say, ask for 2 kbps, which are the networking stuff, I don't know what's going on, but they change the quality, because that's one of the things that are intrinsic to all this stuff. So if the network is becoming lossy, right, then if I can't send the same quality I was doing, I can, for example, quantize the iframes much more aggressively, so the packet size becomes smaller. So I'll still see the traffic coming every so often, but not at the same volume as before, right? Which is different from TCP and other traffic. If you're getting a web document, for the most part, you don't modify the document based on the conditions. You just get the same data. So it's important to understand how these things react, because these are elastic. They sort of comes every so often. And they can place high demand, but they're not usually more greedy than what the network can support. So they're willing to stay within certain bounds, right? So they don't want all the bandwidth they can throw at it, but they would like a certain amount of bandwidth. So they're sort of in this kind of gray zone, right? Yeah.
For the things we've been talking about, is this more a client-side concern or a server-side, or is it both?
It's both. It's actually a network concern, right? The client would be the one who sees a poor quality video. The server would be the one who sends the traffic to you. But from inside the network, if I look at it, it'll look like you're staying within this kind of stuff, right?
So I mean, like as far as like determining, like sending, increasing traffic until you get to like some limit where it drops, would that be something the client's doing or the server?
They both probably cooperate. The server would be the one who affects it. The client would be the one which tells the server every so often, I'm not getting all the packets you're sending, right? So reduce your quality. Right. So if you look at your Microsoft Media or QuickTime and all those things, if you go to the preferences, he'll ask you, do you want to send the state of your network to the server, right? Essentially, your client can say, I'm not getting the quality I want. Can you do something, right? And the server would be the one who does that. But again, it depends on the technology. So we haven't sort of looked at the layered encoding, right? So if I do the layered encoding, then I can do the clients can decide how many layers they need to get, right? So somebody does this adaptation, but once you adapt, you kind of stay within that bandwidth, right? So to make it more clear, we were doing some work on looking at the different kinds of media, like the popular ones are Microsoft Media, QuickTime, and Real. And we took a single video, right? This work was it's kind of dated, right? The 2001 or 2, some like time frame. But the same thing happens, right? So essentially, what we took is we took one video, like our several classes of videos of the same video, made it into a format that Microsoft Media can understand, made it into a format that Real can understand, and QuickTime can understand, and try to see what happens if I'm operating on different kind of network. So I started with 2000 kbps and 768 and 256, 128, 56, and 28.8. These are class of dial-up to DSL kind of stuff, right? So different colors basically give me the network that I'm operating on the client side. In this case, I don't know how exactly this is going on, who is adapting, like you asked. I don't know if the server is initiating it or the client is initiating, but together they are cooperating with each other to reduce the bandwidth that they can get. Because I'm watching the same scene, but I'm looking at it from different client networks, right? So what I'm trying to plot is the packet size that are sent to you, right? So I'm plotting on the y-axis the packet size, and the x-axis has the time. So when I started this video, I'm plotting this. I'm seeing what kind of packets are sent to you. So the thing you notice is if you look at the red line where the bandwidth is pretty high, they actually use a packet size of 16,000 bytes, right? So if you're aware of networks, you can't really send that big a packet because networks typically don't support that packet. So what happens is they get fragmented, meaning like you chop that up into, so let's say 11 different packets or frames, and you send them on the wire, right? So with time, they tend to use lots of packets, and they happen every so often. So they were plotted. So if there's a blank here, then there's really no packet sent, right? So I'm trying to show there's a packet sent here, product packet sent here, but the gaps means that there is no packet sent. So you're sort of seeing a constant stream of packets, and they tend to be fairly big. And once I change the client to be on a slower network, right, the packet size becomes smaller, right? But the dynamics for the most part are the same. You still tend to get, let's say you're getting a packet every 10 milliseconds or so, you still continue to get the 10 milliseconds, but the packet size is smaller as time moves on, right? So from purely from the network side, I'm watching the same video. I don't know what the server is trying to send, but they're adapting in a certain fashion to send packets in a certain fashion, right? The reason why I said that is I'm trying to see is there a general theme to be learned on how these things are sent. So anyway, so this is the stuff for the Microsoft Media. Essentially, you have you do network level fragmentation, but you send these large packets every so often. So then we looked at Real player, right? I think Real is still in business, right? Real was teetering on going under. So we couldn't do the 2000 kbps in Real, but essentially we again did the same experiment with the different kinds of networks. And remember, this is the same video. So if you look at it on the screen, this is going to look to you as the same video, right? But on the network, Real sends it as lot more packets often, but the packets tend to be fairly small, right? Much smaller than what you expect in the Microsoft Media. You see some packets which are 1400, which is a network packet, the network packet size. But you also see packets of all kind of types, right? You see from anywhere from the full packet size to some things which are few bytes, right? So if you think of it as the IBP frames, it's sending I frame, and then maybe let's say sending a B frame and P frame or whatever. On the network, you see the different things going through. So you get lots of these little packets, and not a whole bunch of packets kind of combined together, right? And again, all these things are, I'll go through this stuff and tell you what this could mean. So you see, so the packets are not too big. The packets are what the size you expect, but you're seeing lot more packets of varying size, right? So if you do an aggregate, if you do the amount of data which is transmitted by Microsoft and Real, the aggregate may be the same. So within a certain second, you may send the same amount of data, but in Real, you're sending lots of little packets, whereas in Microsoft, you're sending few big packets, right? And again, we looked at QuickTime. It's kind of hard to see what's going on, but the interpacket time it's more similar to Microsoft than in Real, right? And you don't see as much of a small packets as you saw in Real, right? It's kind of hard to tell from here. But essentially what happens is in QuickTime, it sort of seems to be in the middle where it sends packets every not so often. Maybe it's collecting all the information into fewer packets and sends them on the wire, right? And again, that's the observation we have, right? So they made this decision to do this kind of a packet transmission for whatever reason. The challenge that we were trying to understand, or any system which you build this, using these kind of systems, is that what does that mean for networks with other traffic, other kinds of traffic, right? So if you're at home and you have a DSL link and you're watching a movie streaming to you while you're downloading some stuff, right? Each of these different ways, each of the three different choices would maybe look the same to you on screen, right? But in terms of how they compete with the network, they're vastly different. When you have lots of these small packets, you tend to interfere with more stuff, right? Because you don't, so the way TCP works is it's trying to sneak in one more packet to see if it can get through, right? But if you're sending lots of these small packets, you tend to bump into these other packets more often. The TCP can never kind of expand to take that stuff, right? The other thing you worry about is you want your card to sleep longer, because most of us use laptops, and most of the laptops you want it to sleep. And if you keep sending lots of small little packets, then your card will never go to sleep. So it has implications of energy. It has implications of how it interfaces with other traffic. So even though in the abstract we talk about how these packets, how the I frame and B frame and P frames look, when it comes to the actual how do you serve it on the network, it's still a big issue of trying to figure out how exactly you should do the stuff, because you want to be nice to the other users, but you don't want to be so nice that all your packets are getting dropped, right? So the real way, the real player way, you actually get lot more pay packets through. So you may not see proportionately large amount of quality, but you definitely get better quality because you are outcompeting these things like TCP, which are being nice, right? So from some perspective, it may be a good thing because you're getting good quality. But from another perspective, so if you're at home and you're watching a real movie and then you're downloading something, so you may find that your downloads don't go through as well if you're using Real as compared to some of the streaming mechanism, right? So that's sort of where these two kind of intersect, and the research challenge is trying to make sure that these things all cooperate, right? The reason why we worry about more of those is most of the newer, when you build newer homes and stuff, right? A lot of people would like to get rid of all the wires in the home, right? So you would like to have your speakers connected wirelessly. You would like to have your TV connected wirelessly to stuff, right? So there are a lot of products. There's a number of streaming products on the market, right? For example, one of the products is the Apple TV, right? How many of you seen or use Apple TV or Airport Express and those kind of streaming stuff, right? So the idea here is you want to kind of have your speaker sort of be wireless and have these stream across the house, right? And again, all these things come into play because now you're streaming across your house, and the challenge is to make sure that the quality is good enough for you to replace the cables, but also nice enough that you can do other stuff, right? You don't want your wireless TV to completely take all the bandwidth in your house and you see nothing else, right? But you also want the TV to have good quality because otherwise people don't use that. So there's a lot of research on trying to understand how these things should be streamed and how they compete with the other traffic and so on, right? So that's sort of the meta level stuff of what networking people tend to do and how that intersects with multimedia kind of stuff, right? Networking stuff, people are trying to define notions of fairness, define notions of sending these stuff, but multimedia people have different notions of what they can do. They're a lot better. They need a lot of bandwidth, but they don't need all the bandwidth, and they're able to adapt. So we want to find a good spot where you get good quality, but you're a good network citizen, and where the networking community has this model of you have lots of data, you want to use all the network possible, and here that's not exactly the case all the time, right? And we'll see examples as we kind of move along, right? So I'm going to talk about some of the popular networking technologies. I think the book talks about stuff that is no longer in use. It talks about Ethernet, which hasn't been in use for a decade. The modern network, the Ethernet we use is switched, right? Meaning there's a cable. It's a star topology, meaning from between you and the router. So there's no other competition, right? There are different kinds of networks. I mean, there's 100 megabit per second and gigabits per second. There's a 10 megabits per second, but no one uses those. There's no reason for you to be using that anymore, right? I think most of the NORDM network is supposed to be in gigabits per second, and 100 megabits per second is also common, right? So which means that you have enough bandwidth theoretically to use it for whatever kind of traffic you want to use. The important thing to remember is there is no notion of bandwidth reservation, right? So what we would like to do is be able to replace, like for example, the campus TV networks with the internet-based kind of scheme, right? So if that's what we want to do, if we want to have the TV for all the classrooms and stuff being sent through the wired stuff, right? There's no notion of reservation inside Ethernet, meaning like we cannot say 1 megabits per second is exclusively used for video for inside the campus. They all compete with each other. They all compete with other traffic and stuff, right? So that's an important thing to know. The other thing is on all these kind of networks, if it's a packet switch network, right, meaning that every packet tries to find its way across, the packet size has a lot more implications than you would like, right? So if you're sending 1 byte packet, the amount of work I have to do along the infrastructure to make sure that your packet can keep moving is the same as if you have a 1,000 byte packet, right? So if I'm sending lots of small packets, I'm putting a lot more stress along the system than if I'm sending larger packets. And again, the real thing comes into play. So yeah, so even if I send I don't want to go into all the details about how these things affect. So even if you're talking about gigabits per second Ethernet, if you're sending lots of small packets, you don't really get to go all the way because you're bounded by the number of packets, not by the network can support faster speed, but you're bounded by the smallness of the packets, right? So both of them have implications on how these networks are laid out and stuff. For the most part, you may not worry about it. Most part the network seems to be fine, but OIT still has to worry about if it's trying to send video or audio over the Ethernet stuff, because again, you're taking lots of packets, and it could potentially affect others. You might get the quality that you want, right? And you have to worry about the stuff if you have surveillance video or something going across the Ethernet, right? And frequently people do that. They send videos across the campus network, and somebody else at you, and so because you're not playing nice with the other traffic, right? The other technology which just won't die, and it was sold as a big thing because it comes from the telephony world, is the ATM or optical networking. Optical networking, people who love optical networking love it because it's circuit switched. So I can sort of guarantee, so we can have an optical network within our campus and guarantee how much bandwidth we should give for each of the stuff. So it's perfectly suited for multimedia kind of traffic, right? And though technically it's perfectly suited for multimedia kind of traffic, in practical sense, it doesn't coexist well with other traffic where you just want all the bandwidth. You don't want to go through reservation and stuff. So ATMs are, the book spends enough time on ATM. And it doesn't look like the ATM technology is ever going to catch up. I think the heyday of ATM was in the early 90s. And it just won't die, but it should have been there like a while back, right? So the camp which says that if we can reserve all this stuff, then we can give good quality video, just won't go away, even though the common consensus is, yes, that's good, that you can say how much you should get, but it's good that all these things kind of compete with each other and get whatever they want, right? And there are other stuff, the wide area technology, which is like metropolitan area or something. So you're trying to understand how the network should be laid out, for example, within a South Bend or something, right? There's one paper we'll try to look into that a little later in the course. And it's kind of hard to see what's going on here. But this is the IPTV scenario that AT&T uses. I mean, he used to be at AT&T. The idea here is when they do IPTV, how should the network be laid out, right? IPTV, if you remember, is the Internet Protocol TV, which is what is used by the AT&T US stuff, right? AT&T, their product name is called US. So the idea here is you have a link from your home. If you can see if this is your home, you have a sort of like a DSL, but it's a faster DSL. So it gives you like say 20 megabytes per second. So you have a DSL to something on your street corner or within a 2 kilometers from your house, right? Like sort of like a DSL. And from there on, there are servers as they move forward. The idea here is everybody has makes it look like you have 200 channels or 300 channels or whatever they want to sell it to you, right? So you can watch 200 channels, you can watch video on demand, you can watch pay-per-view movies, all the different categories that you really want, right? But your network here can only support, let's say, 1 channel or 1.5 channel at any one time, right? So the idea here is when I change a channel, I would change my network to get the different channel, right? And if you see, all these things are in like a tree kind of topology where all the people in your neighborhood kind of form one link up to the next level and so on and so forth. So the challenge that they were trying to figure out, which AT&T would love to figure out, is how do we make sure that all the people here think that they have 200 channels, right? So if everybody has 200 channels, and if all of them are watching 200 channels simultaneously, and let's say each channel takes 10 megabits per second, right? What I'm saying is, let's assume that there are 200 houses in your neighborhood, and all of them are watching the different 200 channels, right? Which means that you're going to have 2,000 megabits per second requests out of here, right? If you do a tree structure and do a simple math, right? 200 times 10 is 2,000 megabits per second. So you're going to have 2,000 megabits per second out of your street corner. And that's definitely not the case. I mean, AT&T would like to keep that as small as possible. So the research here is how do you make sure that the worst case, you cannot support the worst case, right? How do you keep these things small so AT&T can still make a lot of money and use your neighbors and all those things, which is some of the things that they try to do. So they like to do some sort of a peer-to-peer and things like that to make sure that you get. So if any of you have a CIPTV base, has anyone seen IPTV based system like a AT&T US or something? So you'll notice that when you change channels, it doesn't change really fast, right? So you may attribute that as you have the converter box, but essentially what it's trying to do is it's trying to change the network topology to make sure you see the next channel, and you tend to get better quality along the way. And we'll see what the challenges are and everything later on. But essentially you're talking about metro area, city-wide kind of network where it may be using Ethernet kind of networks. But now the challenges are different because the way they are laid out. Because in cities, they're forced to lay the cables in a certain fashion as opposed to campuses or whatever, right? And then there's the wireless multimedia kind of technologies, right? I'm not talking about the 2.5, the edge and all those things, which are sort of okay, right? But you sort of need like a 3G kind of networks to get decent quality, right? How many of you used or seen I think the Verizon Vcast, or Verizon has more products on that. I think AT&T has some too, right? Watching TV, live TV on your cell phone, right? So that's their model. I mean, you have about 400 megabits per second, and you like to use that to get video. The nice thing about these technologies are these are more similar to the telephone lines than they are to the internet I talked about. Meaning AT&T, if you have 3G, may decide to give your phone a certain amount of bandwidth, and that's what you get, right? So you're not competing for anything on the last mile. So you get whatever AT&T gives, whatever AT&T your provider gives you, as opposed to other wireless we'll see in the next slide, which is sort of what you're using in your laptop here. In this case, these two laptops are fighting it out to see who gets the most, whereas in the cellular case, you're getting whatever AT&T gives you, right? So if AT&T has 300 kbps worth of bandwidth, it may decide to give you 10 and give you 200 for whatever reason, right? And you don't compete with, even if it's not using anything, you don't get anything, and so on, right? And the other technology which people have been threatening would be out here is the WiMAX. WiMAX is again a broadband kind of network, faster than 3G, so some people call it 4G. And especially on a metro area kind of stuff, right? So in the US, I think there's a company called not Clear Channel or Clear Band or I think Clear Path or something. There's one company which is trying to deploy this throughout the US. Sprint bought it, which is not which didn't make much of a difference because Sprint itself is struggling, right? So they're supposed to deploy it in Chicago like last year or so, and it'll be deployed at some point. It's supposed to give you 768 or 1 Mbps worth of bandwidth, and that would be good enough for you to watch videos and all those things. But again, one of the reasons videos are always pushed on these things are for most normal human beings, right? Meaning like people who are not doing research and doing stuff. If you're at home, you're either doing email or something, and you probably are okay with the dial-up, right? If you want to do better stuff with that bandwidth, there has to be multimedia to drive that, right? Not for probably us, but like my mom or something, right? I mean, she would love to pay for more broadband if she's watching TV or something. So they kind of sort of go hand in hand because the video technologies drive the need for more bandwidth because you want better quality and stuff. So that's one of the reasons why WiMAX was supposed to be a broadband technology competing with DSL and stuff, and the deployment is fairly slow because of Sprint is not particularly healthy in terms of financial situation, right? WiMAX is pretty popular in India. I think WiMAX kind of took over India, though some would argue that they should have done that because they kind of jumped in, deployed it, then figuring out all the bugs with the implementation, right? So those are the sort of the two technologies that providers will sell you to get wireless. The other technologies is what we all use on campus and homes and stuff, which is the 802.11 based system, right? There are a number of different networks. You're probably aware of the 802.11b, G, A, and N, and all those things. Each of them, it's sold that it will give you higher bandwidth, right? B is 11 megabits per second, G is 54, and N can go up to 300, and all those things. And they use spectrum technologies and stuff, which essentially means how they can coexist with your microwave oven, right? So essentially the ABG, the 2.4 gigahertz, it's free to use because that's used by microwaves. So it's not a good band for you to do something that you really care about, because if you turn on a microwave, by definition it will interfere with whatever network you're doing. So it's sort of they try to it's not a guaranteed network like cellular phone, right? The cellular phones operate on certain frequency bands which nobody else is supposed to broadcast, so they get all the bandwidth to themselves. Whereas here they compete with microwaves and all the things you can think of. And there are a number of different networks, variants of the stuff. You've probably seen this with the Bluetooth. People use that for Bluetooth headsets and stuff. And essentially that operates on the same 2.4 gigahertz. So when you're using a Bluetooth, you're competing with your deployed networks and so on. And these networks are much similar to the Ethernet networks we talked about. There is no reservation. You basically try to get how much you can. And I had a little slide on the spread spectrum issue. So essentially, the way they operate, they use redundancy. They use more bandwidth than they have to by spreading the stuff. So if you run a microwave, hopefully it's not spread all over the thing. So you're kind of trying to find out some little area where you can transmit your packets, and you kind of win, right? Because if you don't do that, then if your microwave which is operating on the same frequency that you're trying to operate on, then nothing will work. Whereas this will still survive. Right? I had some slides on the networking stuff, which I'll probably skip, which is the wireless adds stuff that you didn't have in the Ethernet kind of world, right? It operates in a similar kind of fashion, what is called CSMA, which is you try to see if anybody else is talking, and if nobody else is talking, then you transmit something, right? So it's called you sense, right? CS is for sense, and if there's nobody there, you transmit. And then if you detect a collision, so when you're transmitting, you can detect collision by trying to hear what you're sending. If what you're hearing is what you're sending, there's no collision. If what you're sending is not what you're hearing is not what you're sending, then there's a collision, then you back off and do stuff, right? So that's the basic model of how these things work, Ethernet, both in wired and wireless. I tried to look to see if nobody else is talking. So the problem here is all of them are independently making decisions on when to transmit. So each of you can decide that I want to send something. So I don't know when somebody else is going to transmit. So what I'm going to do is, it's the same as like what we do in this classroom, right? So the way that if you want to talk, right, you try to see if somebody else is talking. So if you see that I'm talking, you probably stay quiet, because if you start talking while I'm talking, then we have collision and nobody hears what we're talking, right? But if I stay quiet for a little bit, right, all of you hear that I'm quiet, then all of you have to figure out at some point you have to go. So you can go, right? So hopefully if they're random, then maybe one person decides to go and things work out. But if all of you start to go at the same time, then we get all collision, then we back up and stuff like that. The problem with the wireless is there are conditions where I can't even hear collisions because of the range issue, right? So the issue here is I may be able to hear a certain distance, right? So if I'm talking, and let's say what I'm talking only gets through half the class, and let's say that somebody in the back is talking, they can get to half the class. So if I'm saying something, right, and he's saying at the same exact time, the collision will happen at the middle of the class. So you guys won't hear what we are saying because you're getting the sound from both of us. But I don't know there's a collision because I can't hear him because he's too far, right? So that's the problem here, and you deal with that stuff, right? Because of the range, I can't really know when a collision happens all the time. And that is a problem, and you got to deal with those, right? And there are issues of the other. So there are two kinds of networks. One is ad hoc network, and the other is the access point based networks, which is what most of you are using. So you have certain access points which give coverage. You connect to them, and you get network access, right? Yeah, there are a lot of challenges, and many of them are not particularly unique to us. Many of them are issues of the reliability, security of these wireless networks are not that good, right? And then there's the notion of Bluetooth. I'm not going to go through too much about Bluetooth because Bluetooth operates the same way as you talk about other networks, except Bluetooth has smaller range, right? So the assumption here is I can send a lot more data between my my cell phone and my ear headset because the range is only small, right? So I can potentially continue to talk in Bluetooth while somebody else is talking because the range is very small. And there's push to make Bluetooth work with video and all those things too, or at least stereo and all those things from your cell phone to your viewer. And turns out the thing people like about Bluetooth is it's very energy efficient. Actually, I'm using Bluetooth between the microphone and the camera, right? It's operating on the 2.4 gigahertz, so I'm competing for the same airwaves as you guys using for laptops. And hopefully, I'm not being too bad because the range is only this far, whereas your range is probably 500 feet or so. So I would probably, like my communication probably affects him. Hopefully, it won't affect people in the back, and we're kind of okay, right? So that's the model. But the battery thing here is really important because I don't want to change the battery every day because then it kind of negates the point of me having this headset, right? So you've seen many people have the headsets on for the Bluetooth, right? You want the battery to last long, so which means that you can't have it too powerful and you can't have too much data rate. So you have to compete against those. So if you want to do a video, then I have to send lots of data. That means your battery will run out quicker, and I don't want that. So that's a competing stuff for Bluetooth, right? So that'll give you like a very high level overview of networking. I apologize if you don't fully understand all the issues. I think this level of networking understanding is enough to see what the challenges are, right? So I'm going to actually talk about a paper that Adam worked on as an independent study. Yeah, so Adam worked on this like last year, right? So this is we're trying to see how wireless and games and all work, right? So the goal here was we're trying to see. So you might have seen many of the game stuff, right? Like the PSPs and Nintendos. And by the way, these equipment is still there. So if you want to play with those, feel free to drop by, right? So the idea here was you have these little game gear. How many of you have those Nintendos or PSPs? How many of you use them for playing with wirelessly, right? So what we're trying to see was, I mean, this is part of like some work that people did at like another school. We're trying to see how these things coexist with the existing network, right? So we want to kind of see what happens when you play these games, what kind of packets are sent, and how they interfere, and all those things. And some of the interesting things we found was they don't actually coexist at all because of the unique way that the games are happening and the way the networks are sent, right? What that means in practical terms is if I start to play, and this is mostly on Nintendo. So if we start playing a Nintendo game, right, we don't have to actually do anything. We just have to turn it on, leave it in a networking mode, and leave it sort of on, and it'll kind of destroy all the network around us, right? Not destroy, but it'll severely degrade to the point that you will get much lower throughput for TCP connections, even though we're not actually sending any data because of the way they operate, right? Again, these are sort of things that you want to know because you have these different applications which have different requirements and different ways of operating, and how they interfere is very important because I'm sure, like both of us who are playing games, we don't particularly mind that we are getting good service, but I'm sure all of you will care because hopefully you don't want to be blocked off, right? So this was actually a presentation in Australia, so I had to give some statistics on how big these things are, but they actually sell a lot. I mean, this is in 2007, they were selling like 560,000 units a month in the United States. I don't know what the service is right now, but the rate right now, but they sell a lot because they're not that expensive, right? They're like about $100 for a unit. It's kind of funny because while I was traveling to Australia, on the flight, right next to me, there were like 4 kids playing with a DS, right? And the hostess kept saying that no Wi-Fi, you have to turn off the Wi-Fi, you have to like no network and all those. And we were flying over Pacific, right? So So the airlines would say, don't do that, right? And these kids are playing with the DS, so you kind of snoop and see that they're actually playing wireless games, and you're like, they actually are pretty interfering pretty wildly. But the point is, they don't know what they were doing, right? The same way as if I showed this microphone and the connector to an outside person, they don't realize what's going on, that I'm using 2.4 gigahertz and so on and so forth, right? So if I take this on the aircraft and I'm using this stuff, people don't realize that this is the same technology as the Wi-Fi. So the hostess are more likely to ask you to shut off the laptop than to ask me to shut off this stuff, right? Or if you're playing Nintendo, they just say, you just go ahead, right? So it's pretty popular, and they let you play with people in your neighborhood, and that's one of the nice things. You don't have to pay anything. So some of the games you can play up to 16 neighbors. All 16 of us can have one of the games. Then we can play some games in a collaborative fashion. So if we can play some of the games are not that interesting for me at least. This is like a chat program. So you can write something and everybody can see it, and you can draw something or something. So we can, and there are things that you can do to get animation among these people, but it sort of sounds kind of boring. But essentially, you can have these things. It's one of the popular games, right? So that's just the thing with the things. Actually, we are running out of time, so I'll continue with this stuff. But this is I would rather continue with this on the next lecture because we still have more stuff to look at, right? So if you have any other questions, if not, we'll continue on Friday. Right? Yeah.
What are we gonna do on the days you're not? Or are we?
Oh, sorry. Yeah, on the days I'm not here, we had to cancel class again.
Okay.
I couldn't find anybody to cover those lectures, so sorry, we had to cancel. Thanks.